Hi class. Today I want to talk about, in this video, I want to talk about how we're going to be using Excel to estimate the final temperature in our imperfect calorimeter. So remember I showed this example in the pre-lab video. What you're going to do is you're going to measure the temperature in the calorimeter over some time. Then when the reaction starts, if it was a perfect reaction with a perfect calorimeter, it would stay at the final temperature for a long time. But with a real reaction, it will take time for it to react. And with a real calorimeter, it's also going to slowly start losing that heat, and the temperature will then decrease. So what you're going to do is you want to fit just this linear part of the data to a straight line to estimate what that temperature would have been if it was a perfect reaction with a perfect calorimeter. It can be kind of tricky to figure out how to get Excel to only fit a certain part of the curve. So that's what I'm hoping to show you today with this here. So this represents closer to the data you'll actually get. You probably want to get at least a few points here. Here's showing 6 points. So that's 1 point every 30 seconds, every half minute to get that initial temperature. And I'm sure that with these numbers, you could estimate what that initial temperature would be. The point then is that I'm saying this is for reaction 3, and this is my first trial. And remember, the reaction 3 is taking that solid sodium hydroxide and adding it to a solution of hydrochloric acid. So let's say that at the 3-minute mark, I add my sodium hydroxide, I begin the reaction, and then at the 3-minute mark, then here's the first temperature point that I get. And you can see that the temperature is rising over time, and then after a few minutes, this is the highest time point. And as time goes on, you can see it's starting to cool down. So what we're going to say is that these represent the initial temperature. Here's the reaction still progressing, so the temperature is still rising, and at this point the reaction is mostly done and you're just losing that heat. So the temperature of your calorimeter is going down. So what we want to do is we want to fit just this region of our data plot and then extrapolate what would that line have been if the reaction was instant. And there we can then estimate what our final temperature would have been if it had occurred instantly at this about 3-minute time point. Just as a point, I'm trying to show you good technique when you're showing graphs, so make sure that you have axes labels with the proper units. Here I've titled my graph to be something kind of informative. So one, this is telling me that I'm doing this to determine the enthalpy. Because you're going to make a lot of these, it's also important to keep track of them. So this is the third reaction and the first trial. Remember, again, we're going to be doing multiple trials with these different reactions, so it's important to keep them separate. Now, if we want to determine our final temperature, we want to extrapolate from this point. There's no way to tell Excel that you only want to fit this straight line to that region. If you look, you'll see it's trying to fit all of the points at the same time, and it's kind of a mess. We can't extrapolate data from that. So what we're going to do is we're going to only give Excel the region that we think will be linear. So let me take this and let me show the r squared and the equation right now. So you can see here the r squared obviously isn't great. You want it to be as close to 1 as possible. And it's obviously not fitting the data that we've shown here. So now what I'm going to do is, you can see when I click on our graph, it's showing me the data that it's fitting it to. I'm going to just fit it to fewer points. And if you see, every time I get rid of a point, there's fewer points that it needs for the fitting, and you see that the trend line changes. If I go all the way to when the reaction starts, you can see I'm getting a slightly better fit. But you can see pretty clearly it's curving around the line. So the temperature starts below the line, then these points go above the line, and then it falls down again. So we're definitely not in a linear range. And if you look at the data itself, it's pretty clear that the temperature is still rising here. So we probably don't want to fit the data until it starts to cool. But just to show you what that would look like, if you pick only 2 points, you're not going to have a lot of confidence in what you're doing. So you want to get as many points as you can, where it looks like that fit is still pretty linear. So it looks like I continue adding points. It looks like it's still linear. And if I add another one, here I'm starting to deviate. And then if I add more, I'm starting to deviate more. So let's not keep those points. It looks like the linear part of my graph is only here. I want to point out that I picked these numbers by first starting off with an equation and picking out what temperature it would be. So you're never going to get this perfect r squared. Don't worry about it being perfect. But you're going to be doing something similar where you're going to figure out what region is going to keep you linear. So it looks like for us, it's this 5.5 minutes to 8 minutes. That's our linear region. So what I would do is I would display that line how you'd want. So I'm now changing the trend line here. Let's make it a dotted line. And let's have, oh, I'm not actually changing that. All right, I want this. I want this to be that blue color. I want that to have a dotted line to kind of show that it's a fit. Let's make it a little wider so we can see it better. And then we want that to go back all the way to 0. The period represents the fact that it's we're getting a point every half a second. So you can see if I go backwards 1, it's actually going the full 1 minute. So let's go back a few to make it all the way, to make it reach the 3-minute mark where we added it. So that's a little farther than we need, but you can see that that's extrapolating. That's to the 2.5. It's a little better. So that's extrapolating basically to where the temperature is at the start of our reaction. So this is what we actually want to determine. The way that I would do this is I want to not show those markers. In order to actually reach them, I need to change the trend line because the trend line's in the way of that. So right now I want to hide those markers. I don't want to see them at all. So I'll just make them disappear by making them transparent. Oh, they're not transparent. I made the border transparent. I need to make the fill no fill. Better. So those are disappearing. So remember now that we want, and then now I can't find the markers because I made them disappear. There they are. We only want to fit the 5.5 to the 41.7. So now we have our trend line already there. Then I can re-add the data. Let's do this again. Let's add again the temperature in degrees Celsius. We'll add our x values, which is these time points. Then we'll add our y values. And you see here now we have the trend line that only is covering that linear region, and then we have these points properly shown. And again, remember, if you don't like the colors, we can change the colors so we can have them be blue again or whatever. I think the outline is orange, that's why they look kind of weird. So let's also change the outline. Border, no outline, how about that? And then our goal, remember, is that we want to find out what the final temperature would have been at that 3-minute mark. So you could write these numbers out as shown. Remember, you also have the line est function, and you can do it simply like that. We're going to take the y's again only to the 5.5 point, only to there, and then we want each of these values to be true. Oops. And now we have these two numbers. So now we're going to say that our final temperature determination, we want to find out what temperature, I'll put it down here, where the final temperature was at the time point at 3. Minutes. So what we're going to do is we're going to take, this is our slope, we'll take that slope, multiply it by the time that we're extrapolating to, and then we'll add our y-intercept, and this then gives us a good estimate of what our true initial temperature would have been if we extrapolate back to that 3-minute mark. And then of course if you wanted to find the initial temperature, temperature. You could again do that same kind of point where we can fit this and find out what the y-intercept is. It's probably easiest just to determine the average of those points before we added it. So we can say that's the average. And then when you want to find the delta T, we can then just say it's going to be that final temperature minus our initial temperature. And now we have all of our points. So we have our final temperature in degrees Celsius, our initial temperature, and our change in temperature. All right, hopefully that works. If you have problems with any of this, let us know. We can help you kind of learn how to fit the data. But that should kind of guide you about how I would make this kind of graph to show the extrapolation and show the equation. Some general points about how I would also show the chart and how you can calculate that final temperature. And remember, again, we don't want so many significant figures, so I'd probably bring that down. Okay? Hope that works. Again, let us know if you have any questions.